Okay, so there's four things at the end that sums up everything. All right, so just four things you should be doing to get confidence in real-time positioning. Real-time positioning is great. It's easy. It's fast. Understand, I hope, after what we talked about so far this morning, how many things are happening to make that result occur in your data collection. A lot of stuff. So there's two sets of guidelines that we have: single base user guidelines and real-time network guidelines. The real-time network guidelines are still draft. We had 60 people across the country working on that, some public sector people, manufacturers, things like that. And there's some sections in there for operators and one section for users. The real-time user guidelines are based on single base, but most of the stuff in there is applicable for real-time networks as well. So, that being said, here's some links for it, or you can just go to the NGS website and go under publications and follow it, drill down, and you'll find it under. I'll bring it up later. I'll show you. But basically, it's a long document, but it also has a glossary, which takes a lot of pages. It has appendices that take a lot of pages. Chapter 5 is field recommendations. So that's what you want to remember, Chapter 5. I think we covered a lot of these advantages of real-time positioning. I think the key here, one thing I want to mention as it occurs to me, real-time positioning is really good for a project site in a relative mode with the same initialization. It has been shown in South Carolina by Matt Welslager and others in their public network. They have a whole network of geodetically leveled points too. So you can walk across the state on their monuments, you know. So anyway, that being said, it has been shown by them. They'll go in the field with the rover and initialize, and with that initialization, no cycle slip. All right, they'll hit a point, and they'll go out and hit some more points, you know, as they go. Millimeters difference between those locations. Now, there's a lot going on there, obviously. There's a lot of things to be aware of when you do that. But good conditions, nice conditions, what does that mean? Well, we'll look at some of it. With good conditions, you can get millimeters of difference, relativity with real-time positioning. Same initialization, though. As soon as you lose initialization, all bets are off as far as millimeters go. Okay? Just saying. You'll get a different answer from the morning to the afternoon, but relatively, it should be good. So keep that in the back of your mind. If you look at the different means to get data, especially vertical data, you can see there's a lot of bang for the buck with a real-time network. Geodetic leveling is very expensive to give you millimeters. Differential leveling even, just from a known benchmark, just using a small area of differential leveling. We haven't even talked about gravity today. I'm not even going to get into that subject. But for a small area, gravity is superfluous here. I just wanted to point out that that is the bang for the buck now, a real-time network, and it's going to be getting better and better and better. What you're looking for is simply this. You want that to happen. You want as many satellites as you can get, and you want an open sky, and you want low dilution of precision, and you want a low RMS, all those things you're trying to get. And how that translates in the field is very variable, of course. It's going to vary from shot to shot in the field. So obviously your results are going to vary. Which if you have 8 GPS satellites, now when I say 8 satellites, what does that mean? It doesn't mean there's only 8 satellites in the sky. It means there's 8 common satellites between you and the base station, or you and the network, okay? let me just, as things occur to me, I'm just going to speak them, because even if I have to repeat myself, I don't want to forget them. In single base positioning, you want to set your base station and as open the sky as possible. Very simply, it doesn't matter if this point here is the ultimate truth and you trust that, but you've got some trees over here. Well, I've got 5 satellites. I can do real-time positioning with 5. Let's see, X, Y, Z, time, and redundancy. 5 satellites is what I need for real-time. I can do that. Okay, sure, you can do that. So you set up on your ultimate truth, and then you go over here with your rover, and guess what? There's a row of trees over here. Well, I've got 5 satellites, but I can't do anything. It's because you don't have common satellites. You need 5 common satellites to do real-time positioning. So that's why you need the open sky. You want to get all the satellites you can at the base station. Now, GolfNet, you know they're going to get all the satellites possible. That's another advantage of a real-time network. They're set wide open. So they've got all the satellites they can get. Another good thing. If you're out there, you've got 8 common satellites. If you've got this figure that you're seeing in your data collector called geometric dilution of precision, 1.5, and you're only going a couple kilometers from your own base station, if you've got an RMS of 1 centimeter, and no obvious multipath, you're loving life. You can trust that. You have confidence in that position. It doesn't always happen. So what I've done is just develop, since I work for NOAA, we did to the 7 Cs. And here they are, and the controls at the pole and all of them, so we'll go through them. What I've done is put a B for both single base and network, and then just a blue RT for only the single base consideration. A lot of them are the same. This one is the biggest difference right here. Check equipment. All right, so one thing with both you're looking at here is your rover pole. And you screw the antenna on the top of the pole, and it says, well, it's 2 meters, or 1.5 meters, or whatever it is, 1.8 meters. Well, it may or may not be. At least measure it once. Your antenna may not be seated all the way down the thread. Your point on your pole may have worn. That means you're introducing a bias into every shot you get. Okay, so, we're talking millimeters probably, maybe, but you want to at least check it once. Make sure that the height you got in your data collector is the actual height of your pole to the antenna reference point at the bottom of the antenna, right? So just check it once in your campaign. Now, if you're running a single base, you want to check the base station too, because what they call fixed height poles now are these dowel poles that are collapsible, and you can do 1.5 meters, 1.8 meters, and 2 meters, and slide the dowel through the bottom of the pole and set them up. And you guys use the fixed height poles? Well, real quickly, when we did the Harn reobservation in Maryland, Baltimore County actually had fixed 2 meter height poles. They were 2 meters. They didn't collapse. They were 2 meters. So you had to put them out the window of the car when you drove between point to point. But everybody else had these collapsible ones. It turned out the fixed height 2 meter poles were pretty good. They were still a millimeter or 2 different from what they had the level set up to read. But the collapsible legs with the dowels, some of them were more, some of them were less than the height they were saying. So just check it once. If you're talking heights, you don't want to introduce an error unless you have to. So okay, we're dealing with errors here anyway. Should I go ahead and cover the single base stuff too? I mean, we use single base. Okay, let's just go through it. If you're using UHF radios, get the antenna up in the air as high as you can. So it's good reason to set up on a hill. There's your stats. At Trimble Dimensions, the guy gave a session on this a couple of years ago. And he's just saying you double your height of your antenna, you increase your range 40%. So it gets your antenna up in the air. If you go too far, you need a low loss cable, but that's up above 20-some feet, 25 feet. Of course, the base is secure. If you have problems in your site with topography. In other words, if you have a ravine and you're using the UHF and your base is over here and you're going to the ravine, you're down in the ravine, you've lost your radio. Well, you can have a repeater set on top of the ravine and it just would simply broadcast the signal down to you. Conversely, on top of a mountain. A charged battery for your radio is vital. If you lose power in your battery, you lose range. And know that, well, that's in a communication. You got to have your cables seated correctly. I don't know if this is still a problem or not, but when we were doing static GPS years ago, we did have a setup where you screwed the antenna cable onto the antenna, and back in the office we only had we couldn't process the data. There was only 3 or 4 satellites for this one station. We were scratching our head because we couldn't figure out why. Well, it actually turned out that the antenna wire wasn't seated correctly. It wasn't screwed on all the way. So apparently it was getting the stronger signals but not the weaker signals. So the data from the antenna wasn't reaching the receiver. So just saying. And when you have a base station, you usually have that situation where you have an antenna and then your receiver is down below with a cable attaching. This isn't so important for heights, adjusting the bubble on your pole. But if you're checking a point, as you will do, then you want to know that it's adjusted correctly. This is from Seiko and how to adjust the bullseye bubble. If you don't do it, that's okay. Then if you have to check an important point horizontally, you can just locate it one way and just spin the pole 180 and locate it the other way and take the difference if there's any difference. Of course, you don't want your pole bowed, your carbon fiber pole bowed. But this is mainly for horizontal. What's really important with a real-time network is that the firmware that you're using in your rover is the same as what's used back at the server of the network. I've seen communication problems from the rover to the network because of that. So you want to have your firmware upgraded. Manufacturers love this. Make sure you keep upgrading your firmware so that you have the current firmware available. It's important for communication. Remember, communication's everything with real-time positioning. While you're locating a point, I don't care whether it's with a network or single base, for probably the reason of latency, data latency, you want to have solid, continuous communication at the rover. So you'll see in your data collector, you'll see a little symbol of a radio or something like that, or whatever it may be, a bar, and if it goes in and out, flashes in and out, the communication, beware of that a little bit. So if you're locating an important point, wait or try to get continuous, solid communication while you're locating that point. Once you're done, that's fine. You just walk away. But it introduces noise. I think it's probably because of the data packet delay getting to the rover that it's using older data than it should be using. You got to remember, in a real-time network or single base, that signal has to get down from the satellite to a base or to the network. Then it has to be correct. The signal is corrected, sent to your rover radio or modem, go through that modem into your data collector. The data collector has to make the corrections, or the rover has to make the corrections, and you have to display that result in 1 second, or maybe 2 seconds. But anything longer than that, you're introducing a lot of noise into your solution. And if you go beyond 5 seconds, you're not going to get an answer. So, solid, continuous communication while you're locating a point. Yeah, well, cell coverage, I'm not sure how it is here. There's a lot of areas of the country where cell coverage is very spotty, obviously. If you have no cell coverage, you have no RTN. Very simple. So, and data doesn't always jive with voice. You can have good voice coverage in your phone, for instance, and not have enough strength for data. Okay, so it's not a direct correlation. So anyway, cell coverage is important to know. There may be areas down here that have no cell coverage, I don't know. And also you have to know what carrier works best, right? Whatever it may be. Sprint, T-Mobile, Verizon, whatever. Okay, single base. Good to have a scanner for the signals that you have. You should have multiple frequencies available to you for single base. Because in an urban area especially, like here, you're going to have dropout of the data because of voice over that same channel. So you need to have multiple channels. You can try to lock onto one, and find, oh, that sounds clear. Okay, I'll use that frequency. And of course, as soon as you walk out and you're a mile away, you lose that signal. But at least you're trying to get a clear signal. All right, you're going to do some planning before you go out, especially now with high solar activity. You're going to try to understand if there's anything going on before you go, any warnings for space weather. You're going to look at if there's any time during the day when you don't have enough satellites available, or the dilution of precision goes up too high to be survey grade position, say. And the variable that you'll have to always watch that can't be accounted for in the receiver at all is, well, I take that back. It can be accounted for a little bit, but it's multipath. Multipath is just a reflected signal, right? So anything you're near, even if you park your truck next to your antenna, you're going to have multipath. And you can't account for that directly. How long are you on that point? 5 seconds? 10 seconds? So any kind of reflected signal is going to introduce noise into your solution, or maybe even prevent you from getting a solution, or give you the wrong solution, which is even worse. So that's something you have to, that's experience and knowledge with multipath in the field. Talk a little bit more about that. So what can you plan for? You can plan for this stuff pretty much. If you have a condition like all the manufacturers have planning software, what you don't know is where the rover is going to be. But if you have a corridor survey or you have a base station that you set up, you can plot the obstructions like this one. If you can do that, then you can see what you've got. In this particular day, just using GPS, this represents the number of satellites you have available. Okay, so you can see from 8 o'clock in the morning till 11, you've got spotty satellite coverage. Most of the time it's less than 5 satellites, which means you can't do real-time positioning. That's in that particular spot. If you add Glonass to that, though, you'll have 10 satellites the whole time. So hey, there's the advantage to having Glonass, right? Also, the dilution of precision, which I'll just show you a little slide for that. But generally, you're shooting for, depends what you're doing, but generally, 2.5 or below, or 3 or below. Well, this is off the chart here. It's above 20. So it's too noisy to get a good solution. If you add Glonass, this is a different scale. This is 3 now over here, so you can survey the whole day. So there's the advantage of Glonass. Well, when would that come into play? I'll show you. But generally speaking, it does pay you to add Glonass to your receiver if you can do it. Okay? Does Glonass give you a better answer? No. But it will give you an answer where you can't get it with GPS alone. That's right now. Maybe in the future, it will actually add a lot of precision. It might help in your time to fix, time to resolve the integers. It may help in that. Okay? But the answer itself, the solution, precision of the solution right now is dependent on GPS. There are 2 different systems. I just want you to know this. The satellites that Russia puts up there on a different datum. They're parameters of the Earth 1990.02, as opposed to WGS-84 for GPS. The clocks are different. Okay? So your receiver has to have at least 2 common satellites. 2 satellites from Glonass that it can use, or 2 from GPS it can use. So it can resolve the clock differences and the datum differences. Okay, so therefore, if you have 2 GPS satellites, if you have 4 Glonass satellites, you can survey. Okay, so that's pretty cool. If you have 4 GPS satellites, you don't have enough to do RTK. But if you've got 4 and then 2 Glonass, you can. Okay, so that's the advantage of Glonass. Glonass also is a frequency division multiple access system. That means they have a whole bunch of different frequencies and the same codes. Whereas GPS is code division multiple access. They have a whole bunch of different codes and the same frequencies. So it's very different systems that have to be integrated. And of course, coming along is Galileo and Compass Beidou. As we were saying during the break, most new receivers will have the capability for that. They may not have it natively, but it can be upgraded to that. When Galileo comes along, or there's new signals coming along for GPS, most new receivers are capable of being upgraded to it with a firmware upgrade. Okay, just something to know. And it's worthwhile. This just shows you that there's now a full constellation for GLONASS. In years gone by, they would shoot 3 up at once, you know, and 2 would fall down. And they'd shoot 3 up and 2 would fall down. But they've got a full constellation now that you can use. So it's going to be an advantage in an urban environment where you have urban canyons. It's going to be blocking satellites, road corridor surveys, or maybe you need an important point between 2 bridge abutments or something. You've got to get that sanitary manhole. So you're there and you don't have enough GPS satellites, but with GLONASS you can get the shot. So that's the advantage of GLONASS right now. Now as far as DOP, dilution of precision, that is very simply the geometry of the satellites overhead. So here's what it means. If the satellites are close together up there, and of course this is only 2 satellites, but if they're close together, that red area is the spread of the solution area where they intersect. Okay? If they're spread apart, the green area is much smaller. So a dilution of precision is a unitless number. It's just a relative value that was used at one time to multiply the error in the code phase. If you had a DOP of 2, you'd multiply the error by 2. You know, but in real time, we look at that as a relative value, and we say, don't do real time for precise points if you got more than 3. Position dilution of precision. Now, PDOP is horizontal and vertical. GDOP is horizontal, vertical, and time. So it's all dilution of precision. Okay, and that's a figure that you can also plan for your base, or if you know where you're going to work. You know, you can sort of plan the general area and see what your PDOP is going to be during the day, as well as your satellite count. Now, constraints. This is where people that use real-time networks now are calibrating or localizing to monuments in the ground at their site. You can do it horizontally, vertically, or both. Most real-time networks will give you excellent horizontal results natively. So it's usually not necessary to worry too much about calibrating, except if you expect different results. If those monuments, maybe you're not sure if really the values that plan says are going to match the network coordinates, then you can do a localization to those monuments horizontally as well as vertically. Okay? The idea is, and it's not going to work great down here because there's not enough monuments that you trust, but the idea is you surround your project with at least 4 monuments in a rectangle as much as possible. When I was in the private sector, we had a job. The party chief went out and located 4 monuments to calibrate the site. But the trouble was, about a week and a half later, the engineer said, you know, this sanitary sewer is 4 feet, seems to be 4 feet out. We don't know what's going on. You know, and here's the plan, and we're getting 4 foot different elevation. Okay, so what happened, we talked to the party chief. He hit 4 monuments, but when he hit them, he hit 1 here, 1 here, 1 here, and 1 here. So what did it do? It did an adjustment of all 4, held all 4 values, but he typed in the wrong value for this one by 8 feet. The one sitting out here by itself. So instead of being where it should have been here, it was here. So what did this do? It said, oh, I can do that. I'm just a hinge. So it swung up like that and did an adjustment to all 4 of them. And it worked fine between them, because these guys just were acting like they were on a hinge. They just went like that, and they did the adjustment. Everything was, oh, okay, it looks like it works all right. It's a few hundredths. But if we'd have looked at the slope of the vertical, we might have seen that. But anyway, so you want to have, as much as you can, a rectangle, so that if something is piped in wrong, you know, you don't get a bogus result, even if it looks like a good result. So you can hold those values of the marks. Now what does that do? All right, it locks everything. Cliff.
We have a problem in Louisiana in that we've got thousands of benchmarks.
Right.
In the metropolitan area, we've got over 500.
Mm-hmm.
But because of subsidence, there are only a certain number of marks that are regularly updated by NGS. And those are constrained in terms of time. Each one is a group of benchmarks that are observed, and it's a snapshot of time.
Right.
And we call those epochs.
Right.
The first epoch was done after Katrina, and that was 2004.65. You all recall. When you calibrate, you have to calibrate within the same epoch. Because then they also came out with, what was it, 2008? Another epoch. And then since then, NGS has observed a third epoch, but they have not released published values on those yet. So that when a surveyor does a local calibration, he has to maintain his calibration within the same epoch. You can't mix and match.
Excellent point. Excellent point. So you understand what Cliff was saying. Different adjustment, right? So you got to use the same thing. You got to use the same. You got to use the same datum, the same adjustment of that datum, right? And the same snapshot of that adjustment. So that's what Cliff's saying. Good point. Thank you. And most real-time networks in the country are doing something like this for their verticals. The guys go out there, girls, guys. If they're doing surveys, they go out and they find monuments around the site that they trust. Hopefully, maybe one in the middle of it or something. And you just visit them with GPS. So what are you doing? You're putting WGS 84 XYZ coordinates on those monuments from the satellites. Then you're typing in what you want them to be. You can assume coordinates as long as they fit together. It's not, you don't want to do that, but and so then you're typing in usually state plane values for them or something like that. You type them in and you hit the magic button. And when you hit the magic button, it does a least squares adjustment and best fits a plane to those monuments. So now what have you done? Well, if you typed in state plane, you've taken the grid values and stuck them on monuments on the ground. But that's okay, because now you've constrained those values on the monuments, and everything you do internally to them is going to be relative to them. So that when you get a state plane value here, and you actually took it down to the ellipsoid and squashed it flat again, it would be okay. So what you're doing is taking the state plane values and fitting them to the ground, so that, you've taken the state plane values and put a best fit plane on them on the ground. Is what you've done, basically, for your project. Okay, if you calibrate. Also, what you've done is you've got a great way to check the precision and how those monuments fit together, which sounds like a great idea for Louisiana, which everything's subsiding. So when you hit those monuments and you do an adjustment, it'll give you the residuals of the adjustment. So if you look at one of them and it's out 3/10 of a foot, then okay, well, all right, does that mean that one's right and these are wrong, or these are right and this is wrong? That's that's why we get the big bucks, right? So that's what you have to decide. But at least you can see how they fit together, which is a good thing. If you're doing work and you've calibrated a site, two things are very important. One, you work within the calibration. Don't go outside the calibration, or you're extrapolating a solution, just like going outside the state plane. And number two, make sure that everybody in the field uses the same calibration and the office uses the same calibration. Because if you don't and somebody else does another one, you're going to get bogus results between them. So those are two things you have to do with the calibration or localization. You can do it, by the way, you can do a 2-point localization. I say 2-point because you hold one monument as truth, right? Vertically. Say, here's the elevation, this is good. And then you have another one across the project you can check. Okay, that checks. So then you have, what you've done is said, this is it, that's truth. And again, real-time networks give you good horizontal. The vertical is what you have to work with. hopefully, well, we know for sure in 10 years when they do the new datum, you know, you can bring 2 centimeters to your site. Yeah, we talked about good relative positions. How good is the geoid model? We know it's not so great here. Geoid 12. Geoid 09 is what you probably should use. Yes, sir.
Bill, can we go back to something Cliff said, and Cliff can address this or anybody else who wants to. But you said it was an important point that you constrained to marks that were all, say, 2004.65 or to whatever. But if it's something as old as 2004.65, that's 8 years old, and we supposedly have differential settling. All marks in South Louisiana have a velocity, different velocity.
Probably 5 centimeters different.
I mean, so, how do you know you don't have differential settling within those 2004.65 marks? So it seemed like you should say use the most recent marks. I mean, because rather than use all marks of a certain age group. So, but you said it was important what he said. So if we could just maybe.
The important thing is not to go across the adjustments. I mean, that's what I was saying. Don't use half of them in one adjustment and half in the other adjustment. You know, what Cliff is saying is make sure everything's homogeneous together as it was constrained. Your point is an excellent one also. Use the most recent adjustment of it. That would make sense. I'll tell you, it's scary here. I mean, what do you use? You know, that's the thing. How do you verify it?
Yeah, my suggestion, and tell me if I'm wrong-headed here, but my suggestion would be if you have this old mark problem, that you have to, by static observation, establish your control network around your project site, and then run your constraint.
Yeah.
And create for that project your own data based upon static observation. It makes you work a little longer, but at least you have something that you can hang your hat on, so when the lawyer drags you in court, at least you can have something to add to the confusion. But well, that's what you're trying to do.
You get as much justice as you can afford.
That's right. But yeah, the differential subsidence rates here are absolutely profound, staggering, terrifying. I hope I can't scare you enough.
Yeah.
But the most rigid point that I know of has a subsidence rate of about 0.2 of a foot a decade. Cliff probably knows the one that's better, but I think it's in Kansas. It's it's scary. It's scary. So you're looking at probably to do a constrained project. Let's say building something fairly big. I would suggest 4 static points around it, and then run your RTK static constraint within those 4 points. Anybody got a better idea?
I think the criteria is what is truth for an elevation. You
We don't know.
Alcoa.
Yeah. Alcoa. So
That's just one more.
you guys know the answer to that better than I do.
Yeah.
How much is it going down, Dave?
6 feet.
You got to hold something, right? You got to hold something.
Before we had the NGS capability, the way I used to check marks was I used to go to the waterway and shoot the elevation of the water. And because I knew that water was going to be up and down about a foot, so I could pick the ones out that were 5 feet out. I could say, well, I'm not going to use that mark. Because I know Lake Pontchartrain isn't at +6 today.
It's.
They think I'm exaggerating. They think I'm joking.
I would suggest that probably the RTN stations using geoid model geoid 12 and the excellent ellipsoid heights that they have, probably the error in the ellipsoid height alone is probably well below a centimeter, maybe 3-4 millimeters. Geoid error might be a centimeter. I would say that the stations themselves might represent your best value of current in AVD 88. Now, how do you get that antenna value to your site?
Yeah. The specs read NAVD 2004.65,
Yeah.
88.
Yeah.
So
Right.
the question is,
Right.
how do you recreate that?
Yes.
How would you recreate it?
Yeah. I think it would be site specific. I think if there was a bridge that I had to tie a road into, I would hold the bridge.
Yeah, but
If there was a
not,
sewer
you build
line
levees
that I had to have houses built to drain into, I'd hold the sewer line. You see what I'm saying?
I
Pragmatically.
understand that.
you know.
I do understand that, but I'm saying if you had to recreate NAVD 88 2004.65,
Yeah.
which I think is the question of the day, how do you do it?
Yeah.
I don't think you can.
Well,
Okay.
you can, but to what accuracy? You
Well,
know,
it's got to be plus or
How
minus
would you
100
do
foot.
it?
Yeah.
Is my question to you.
I would look at the area I'm interested in and the published marks from that adjustment. Then I would do a comparison between them. I would use RTK for it. And I would do a comparison, and I would look for outliers. And if there was any outliers, I'd have to weigh whether I'm going to discard them or whether that looks better than the other ones. So I'm assuming that would be an outlier. So I would throw that out. Then I would do a localization based on those marks, and I would hold them. That's what I would do.
Couldn't he calculate the velocities to, if he's trying to get, you know?
Yes and no. You can. However, velocities aren't linear, which means it could subside 3 millimeters this year and then a centimeter and a half next year. Okay? So, another variable.
Well, other thing too is 2004.65, there were only 99
Yeah.
for all of South Louisiana.
Yeah.
Okay, then the next epoch, there was 300 of them. And then this.
Right, 300 is what I remember, yeah.
I believe we're back to 99.
Okay. Well, are they mostly deep line marks, Cliff, you know? They're like that, or are they like this on bridges?
Mixed.
Mixed, okay. Even the deep rod marks, though, are not driven to refusal. I mean, they went down so far and said, I give up, you know, that's it, you know? And they're not on bedrock. I remember Roy Dock saying that. Yes, sir.
Would be a fair statement too, that, I mean, the accuracy is that people would accuracy, so going back and forth, you know, a lot of people in the past, we deal with hundreds in their head. I don't
Yeah.
think we're, the days of hundreds are gone. I think it was, might be 6.2. We're just saying plus or minus 10.
Yeah.
Or
Yeah. Yeah, I mean, pragmatically, I would try to hold the benchmark values, but in the field, I'm going to make sure my construction ties in.
Yeah, relative to what you call the truth.
Yeah.
The truth is plus or minus 10.
You're going to meet,
Relative to.
if there's an existing curb there and you stake out more curb and gutter, you're not going to build it 3/10 higher.
No, you can be relative.
You're going to hold that end of the curb. You know, and we've seen this in little jobs and where I come from, that, I mean, you got to do that. I mean, elevations are there, but they're almost superfluous of what you're going to hold. You got to hold construction. So that comes into play too, you know. I mean, puristically, we're looking for a puristic answer to a pragmatical problem. And I don't think we can do it. Not yet, not yet. Maybe when they're done with this process, it'll work for a while. You know, but then it'll only be a while. I would like to work it for the next 10 years, and then we can just
Yeah.
jump to the new date and we'll be all right.
I just
So-
think it's important to document.
Yeah.
That's our main.
Yes. Yeah. Absolutely. This is part of a geospatial professional, I would say land surveyor's book, is to know how to make things work. It's not easy, always. And I guess we know that today. It's not easy. So you got to meet something somewhere. And that's where the bottom line is what you're going to build, or what's going to happen from there. You know, boundaries are horizontal. You know, you can work with that, except for high water. You have to establish that. But anything you build has that vertical component to it. So, you know, it's not a matter of relative precision, it's a matter of what is the elevation. So to make the relative precision work with the existing construction, the way it works out. Anyway, this is like if you had state plane values and you did a calibration to those monuments on the ground reflecting these coordinates, then you have those coordinates on the ground. Okay, you squashed everything, you squash things together and spread them apart. But you're holding those values. Okay, so now everything you've done would create a state plane coordinate unless you change those coordinates. Okay, you have to be careful. DOTs do that, and then what they do is they truncate the coordinate so that their road work has local coordinates. Now, they have problems when they fit roads together. You know, it's endemic. So here's a calibration. This is, again, my old software. And you hit it with a GPS, you type in the value, hit the button, and it gives you maximum residuals, okay? Gives you a vertical inclination, and it gives you a scale factor. Scale factor should be around 1. And then you can also look at the points individually. As you hit it with GPS, the calculated point and what you typed in, okay, and the residuals. So that's where you can evaluate the control, how it fits together, which is a good thing. I can't bring this up on the net, but here's the address for it. And what this is a blunder check for your work, sort of. It is a blunder check, because you're not looking for a millimeter, you're looking for a half a foot, okay? So when you hit a point, and you've done it with the real-time network, and you're not, you know, you don't see any stations when you do that, right? You sure have there, here's my point. And how do you know whether you actually did something stupid or not, you know, like me? Then one way you can do it is get 15 minutes worth of data on that point and send it into the NGS OPUS RS and get a result back. And when they send it back, it'll be geoid 12 and your ellipsoid height. But the orthometric height you get back is a nice blunder check. If you've got 2 centimeters, you know, you can't rely on it for that. You know, if you've got a foot, you've done something wrong. Okay, so it's a blunder check. It's not a precision check. But it's a good way to check. And you can actually go around the country and just click, you know, blow this up, zoom in and click on Louisiana or New Orleans, whatever. And you could look at the north, south, east, west expected accuracy using OPUS RS and 15 minutes worth of data. 1 sigma, again, 65% confidence. And then you can change that to ellipsoid height. See what kind of ellipsoid height you ought to be able to get back based on 15 minutes worth of data or whatever. Again, 65% confidence. You got to double it. But you can do that. And that's a nice blunder check to have once you've done a job with RTK. And just go to one of your control points and get 15 minutes worth of data and send it in. And when it comes back, okay, 2.5 tenths, you know, that's possible. But at least I know I'm in the ballpark. That would make me feel better anyway. Okay, coordinates. Garbage in, garbage out if you're using single base. Type in the wrong coordinate for the base. Every coordinate you get from that base station is wrong. Right? Wrong. We mentioned this. Know what datum and epoch you're using from the network. Know your quality of the geoid. We know precision accuracy. When you use RTK from a network or single base, always get a check shot before you do anything else. I don't care if it's a MAC point or an elevation off of a road drawing or something. Whatever it is, whatever the most accuracy you have, check that point before you do anything else. You could have a bad initialization. Then every point you get from that initialization is wrong. So it's a simple thing to do, but you need something to check. So I don't care if you got that point yesterday. Go back and check that point. You know? Oh, okay. But do that first. You can do single base positioning with an autonomous coordinate. because everything's relative. It's X, Y, Z, right, from the base. Difference in X, Y, Z. And then all you do later is in the software or in your data collector, you type in the right value for that point that you've gotten, and it just takes all those vectors and shifts them over. That's all it is, just shifting them over to where you go. No rotation issues because it's the project area. You're not going across the country. So you can do autonomous setup and just type in the right coordinate later. Just so that you think about that. Let me just see. Collection, okay. You're going to check a known point. If you can, after your session and during your session, maybe an hour apart or something. Don't be afraid if you get a different answer. It's just you don't want a big different answer. Okay? The thing about redundancy and multipath, if you're doing static GPS, multipath or reflected signal is cyclical. That is, it changes every 20 minutes or so, like a sine wave. So your software can model that and take it out. But if you use an RTK, you're only there for 5 seconds. You don't have any capability of modeling multipath. So there are some rejected signal firmware and hardware in your antennas, but still you can have multipath. You can get a bad initialization, so you need to check something. That's why you're checking things. That's also why you want redundancy. Not just to say you get the same answer. You're probably going to get a different answer. Multipath is going to use different satellites. Redundancy is going to use different satellites. So when you come back to that point, you would like to come back 3 or 4 hours later or the next day or in the afternoon or some other time when you're not using the same satellites. Get another shot there if it's an important point. And your best answer is usually the average of those 2 shots. Not this one and not that one. Usually it's the average of those 2 shots. That's the best answer. Okay? Different satellites, different multipath. Okay. Also, obviously, you need to enter in the right antenna in your data collector. If you don't put in the right antenna or receiver antenna model, you could introduce a decimeter in your heights. You could. Just saying. You also want to know that what you're looking at, your data collector, sometimes it depends on the manufacturer and what's set in there. But a lot of times what you're looking at is 65% confidence. Right? Your horizontal precision, your vertical precision, and your root mean square error. By the way, root mean square is just the spread of your answer. Okay, that's what it's going between to figure out its answer. Okay, it's probably taken, I don't know, I think it's just an average, I guess, of the data it's calculated. So if you have a big RMS, it means it could be anywhere within here. And it figured it was here. If you have a small RMS, there's less play in that answer. Okay, so small RMS is good. So, but understand that both the RMS and precisions are usually one signal, 65% confidence. So you're going to have to double them to really get a sense of 95% confidence. Okay, just saying. Let's see. Some manufacturers have the covariance data toggle on. Some don't, and you have to enter. You have to say do this. Trimble is like it's. I can't remember the number now. I think it's Q2 or something like that. Whatever it is, it's one of those things you set to turn on. All that's doing is creating an error ellipse, if you will, that you can dump into the software. You can see the error ellipse on your point. If you have a redundant shot on that point, or if you have a shot on that point from a different baseline, a different base station, or whatever you have redundant data on that point, you can actually post-process, well, you're not processing, but you can adjust that position based on the 2 shots together, rather than having 2 separate shots. Okay, you can average those shots together if you have the covariance matrices toggle on, or whatever they call it. It depends on the manufacturer. We talk about fixed and float. I guess pragmatically, we talk about latency. Okay, so you're talking a second or 2 latency in the data. You know, you can do as-builts with real time. You put wheels on the bottom, run along a curve or something like that. Just understand that as you're getting your as-built, it's 1 second behind you that you're looking at, okay? Because of the data latency is the solution. So if you've got an important point, say a sanitary manhole, and you've got some trees over here with some canopy. Oh, by the way, still true. Friends don't let friends RTK under canopy. I don't care what you say. I got 3 millimeters. Well, yeah, go back there again. Oh, I got 3 feet. Yeah, that's right. You don't know. So carrier phased, don't do it under canopy yet. Don't do it yet. Maybe in the future. All right. So you got an important point here. A sanitary manhole. You got some tree cover canopy, and you're out here and you're okay. I'm fixed. All right. You walk in here to the. You lost law. Then you go back out here. Okay. Fixed. Got it! No, you didn't get it. You got the shot out there. So it doesn't work that fast. There's a latency. Just understand that. The only way to try to get that is to try to sneak in a little bit. And maybe you can get on the edge of the rim or something and get a shot there and then, you know it's about 1.5 foot over or something. You know, you just have to try to sneak it. You can't run. It doesn't work that way. I've seen people do it. Okay, when you have an important point, do a blunder check. Not by OPUS, I'm talking about. I'm talking about just taking it, lose initialization, reestablish initialization, but do it over here. Do it 100 feet away from your point. Different multipath conditions. Reinitialize. You can, do it in the data collector, turn off the satellites, turn it back on, whatever you want to do. Reinitialize and walk back over to your point. Hit the shot again. Does it work? Does it compare? That's a blunder check. You want to do that for important points. That is not the same as redundancy. I mean, it is redundancy, but it's not what we're looking for. Redundancy is with different satellites. Okay, so you haven't changed anything in the parameters when you've just got another shot there. The only thing you've changed is initialization, which you've already checked. Okay. Sometimes you use a bipod if you've got, you've got to be there for 3 minutes or something. You can set up a bipod so you don't have to sit there and try to hold it steady for 3 minutes. This is from the guidelines in Chapter 5. Made this up to try to give people some criteria to achieve certain accuracies at 95% confidence using single base. You could probably get away with doing less than that. But I guess what I'm saying is, if you do that, you will get those precisions at 95% confidence. So the highest one is this one, where I'm saying 1.5 cm horizontal, 2.5 vertical, okay, to the base, okay, whatever it may be, assuming the base is the truth and its accuracy. If you don't know whether it's true or not, then it's precision, but to the base. And then saying get 2 locations with different base stations if you can. All this is ideal. But if you can use a base station on this side of the project and one on this side of the project for the same point at different times, that's great. Then you improve your base stations too. Always be inside the calibration if you've done it. Here's your position, dilution, or precision, 2 or less. That's from your data collector you're looking at. RMS, your data collector you're looking at, centimeter or less. Collect it 1 second for 3 minutes. Gives it time to settle down, make sure it's got the right answer. One good thing about real-time receivers these days is if for some reason it gets a wrong initialization, it figures out the integer is wrong. As those satellites move a little bit, at 8,400, 9,000 miles an hour, it'll be continuously updated. And it'll say, whoa, something's not working here. And it'll reinitialize. So that's why 3 minutes is good. It'll give it time to settle down. It initializes. If it has a problem, it'll reinitialize. And it gives you a nice set of data. So everything in real time is about movement. Those satellites and same with static, of course. So GPS positioning is differential, so it gives a chance to change. Try to get 7 satellites if you can, and don't go any further than 10 kilometers. Now that's for single base. Obviously, with a network, you're not going to have a base station per se. You can still look at your satellites. Always more satellites, the better. And PDOP is important. Also, the 2 things you can do with a real-time network are check your common satellite, well, 3 things. Common satellites, the position, dilution, or precision. Number of satellites, position, dilution, precision. How many common satellites you have. What else can you check? Well, check your RMS. But I think your precisions are what you're going to look at with a real-time network, horizontal and vertical precision. And that'll give you a really good feel for what you're doing. You're trusting the data from the network is what you're doing. So anyway, the lowest class would be like a GIS grade, decimeter and a half and 2.5 decimeters worth. All right, confidence. Okay, here's the scoop about redundancy. In order to have confidence in a real-time position, you need redundant location. The University of Newcastle has done a study in England using their network, okay, a real-time network over there, and testing it with a couple different receivers at certain points. Now these points were wide open, and it was done in the spring of the year at a certain latitude. They said, we didn't see any advantage to going beyond 45 minutes to get a redundant location. So they were saying, you can come back in 45 minutes, get another shot there, that's good enough. Be that as it may, I say that from the Gulf Coast at sea level to the top of the Rocky Mountains, to Alaska, to Florida, to the East Coast, to the West Coast, I say there's a lot of variation there. And I say that it's better to get different satellite geometry than it is to get a shot 45 minutes later. It eliminates the same multipath condition you had from the first shot. It gives you a completely different multipath condition. I say because of that, for the USA, I say it's still worthwhile to get a redundant shot 3 or 4 hours later, or a different morning, afternoon, or something like that. Okay, come back the next day at a different time, whatever. But it's worth it to do that, I say. So that's what I say about redundancy. You still want to do a blunder check for important points. But high tension lines. Can you real-time position underneath high tension lines? Yes? No. It depends. It depends how much current is going through them. So I've been on both. I've been under high tension lines where there was no problem at all with communication using UHF radios. The data looked good, you know, RMS looked good, precisions looked good. The shot seemed like it turned out okay. And I've been underneath high tension lines that I can't communicate with the base. So I had no idea what I got. So I think it's about how many hundreds of thousands of kilovolts or whatever it is they're sending through that line. And it could be time dependent. It could do it like in the evening or in the morning or something. So it's completely variable. That's something that you can't make a recommendation for. Just know that you could be a problem, but if you get an answer, usually it's okay if you use your precisions. And if they look okay, usually you're okay. That's all I can say. If you're using calibration, make sure you're inside the calibration. If you're using single base, remember it's part per million error. Okay. Another thing that seems to work pretty well, if you're out and you're trying to initialize, you're doing the ambiguity resolution, your receiver's working and it's working and it's working and it's working and it's working, and it's just not happening. And you have GLONASS turned on. Try turning GLONASS off. Okay, then just try it with GPS alone, assuming you have enough satellites. You know, you have 5 satellites or more. Try just initializing with GPS. Sometimes that doesn't. So another thing to beware of, though, if you have plenty of satellites Even, say you're not using Glonass, but you're in an area where it's taking a really long time to initialize. It's still float, you know, you're there for a minute, you're there for 2 minutes, float. Then after a couple of minutes it goes fixed. Beware of that shot. That means your receiver was working really, really hard to try to figure out that integer count. And yes, maybe after a little bit of time it'll reinitialize, but maybe that's the last shot, or maybe it's maybe you're going to lose initialization anyway to get to the next shot. So you don't know. You know, you don't know what you got there. So beware long initialization times. Also, you can also actually check your data collectors if you're having trouble and see the satellites and the signal to noise ratio of the satellites. If there's a very noisy satellite, you're not getting much signal coming through, turn it off. If you've got enough satellites, if you've got 7 satellites, turn one off, it's noisy. That might help you initialize. So those are a couple things you can do. Here's some examples of multipath, no big deal, just showing you different ways you can get it. There's a couple different kinds. This guy has multipath. I hope you don't mind one more war story. We were doing some piling cutoffs for Baltimore Washington International Airport, a barrage they were building. I was in Providence. And they had these big rebars, different quantity of them out of each big piling base. And we were supposed to as-build them to make sure they were cut off right and everything. And we didn't have a robotic total station at the time, so we used real-time positioning. So the party chief went out there, and everything was going fine, and he'd send the things in, and we'd make the drawing up, and I'd sign and seal it, and it'd go off. Well, about a week and a half later, the super from the job calls up, hey, you guys got 4 inches wrong in this elevation here. These aren't right. Oh, what? Well, no, we checked it. It's wrong. Oh, okay. So bring the party chief in. Did you have any trouble out there or anything? I mean, he said, no, I don't think so. Well, I went out, and what happened is this. He was at this one particular piling base, and as he was standing there trying to get these different rebars on these piling base, they're driving pilings next to him. And the pilings are like 25 feet in the air. They're steel I-beams. So he had multipath bouncing off of that. Plus, the guy's out there with a pile driver going boing, boing, and the guy's going boing, like this. And the poor receiver was trying as hard as it could to figure it out. And it came up with an answer that was wrong. It had the wrong initializations, and there's your 4 inches, And so, multipath and, stability, but multipath. So this is what your receiver would like to see, the signal coming in, and this is what it sort of sees, the multipath. That blurred image gets a lot of noise in there. Real fast. I mean, there's direct reflection off of signs, trucks, buildings, things like that. There's also diffuse. Like if you were going along the shore of a Pontchartrain or something, you'd have multipath coming off the way, believe it or not, but you would. So even a road will give you multipath. This is like trying to figure out the number of cycles. It's just a little cookbook here, kind of what to figure into. And it has like the copocentric range of meters, and it has the clock errors in the receiver, and the clock errors in the satellite, initial cycle count estimate, the ionospheric error, the tropospheric error, the hardware noise in the receiver, the hardware noise in the satellite, white noise. White noise is just the internal electrical, I guess, kind of a resistance that's going on inside the receiver. And for high-grade receivers, it's superfluous. It's, millimeter or something, so it's not to be worried about. But that is multipath, okay? Can't be eliminated from model. Real time. So it doesn't go away. And you can see that by introducing noise and reflected signal into your receiver, you can get a bad answer or a noisy answer. So that's where you have to watch out, Stay away from canopy, stay away from reflected signal. This is just to demonstrate redundancy. I don't really get into this too much. This was done for the core system for the static guideline. They took the core's data, they divided into half-hour sessions. They took, say, 8:30 to 9 on this day, and 8:30 to 9 on this day, and compared it to the truth, and they came up with a difference of only 3 millimeters between the 2 days. But the actual difference to the truth was 2.3 centimeters. Okay? When they went in there, they took this same day here, but they compared it to 2:30 to 3 the next day. They compared 4 centimeters between them. Sounds worse until you take the average, which compared 1 millimeter to the truth. So that's where they got that from. Different times of the day for redundancy. And that was, what, 16 years ago, I guess. So equipment's a lot better now. But that's what I'm saying, maybe we ought to keep that for a while. All right, in the office, you can check some stuff. You're not going to change much, but you're going to see if they use the right antenna. You're going to see what the precisions were, you know, things like that. You can look at the coordinates, make sure they use the right coordinates. And you can do that when you dump it into the software, which I hope somebody here today can do with Trimble Business Center. And you can look at stuff like this. Here's the PDOP that was taken at that time. 3. And vertical precisions, what, 2 centimeters, 1 centimeter horizontal precision. Slope distance, satellites were 7. So those sort of things you can review in the office. Here's some other things. The antenna, the time of the session, or the baseline. Here's the XYZ. Now we know what that is, right? The difference in XYZ from the base to the rover and WGS 84, which incidentally is the same as 93 in this case. Not true. And northeast and up, and the azimuth and the difference in height. Okay, this is just to demonstrate, most of you know this, I think. 2 different antennas will have 2 different electrical phase characteristics. Because the phase center is electrical center, it's not a fixed physical center. That's why we use the antenna reference point instead of the phase center. So 2 different satellites or 2 different antennas will hit that phase center at different spots. You can see the phase center for both of them. You can see that it hit that electrical characteristic in a different spot. That's why you get differences between the antennas. Another thing to consider, if you're doing a lot of real-time work, and you have some crews out there or something like that, it's, you know, what you get with real-time is coordinates, and you don't get much else. So what might be good to have is some kind of a sheet for metadata. What the day was, what the technician's name is, what the antenna was, are there any notes to be made about things that happened or anything, you know, how long you collected data, things like that. If you used GolfNet or you used your own base station, something like that. So that you have some metadata to go back to. Oh, okay, well, this is good. We can go back and see what that is. And just to emphasize that, this is, you know, you have to stop and think about this. This is a superstructure on a boat, a ship, excuse me, going underneath a bridge. This is actually in Oakland, California. They just did it in Chesapeake Bay, by the way. But think about what has to happen there to get that underneath that bridge. You have to know, first of all, about the bridge, don't you? Well, what do you know about the bridge? Do you know what datum it was staked on? Do you know where it is? Do you know what the elevation underneath of the bridge is? And what's it based on? NAVD 88, NGV 29, assumed datum, tidal datum? How about the channel? What's the depth of the channel? How about the tides? What are we going to reference them to? How about the ship? Where are the antennas on the ship? Superstructure, the keel of the ship. What's the squat of the ship? The faster a ship moves, it squats in the water, you know, pushes the water aside. So what's the speed of the ship? All those things have to be taken into consideration in order to get that thing underneath the bridge correctly. And that's a lot of metadata, but let's see how important metadata is. Actually, it wasn't important, clearly, you know. Okay, so did we talk about all this? Let's see. I think so. Oh, we didn't talk about that mask. Very, very quickly. it would be nice to collect all the data you can. But the problem is the data nearest to the horizon is the noisiest data because it has to travel the furthest through the atmosphere. So we can get by with cutting some of that off. You can't cut too much off or you don't have enough data. But the happy spot's usually 10 to 15 degrees. So I would recommend 10 degrees and cut off the data below 10 degrees. Call it an elevation mask or cutoff angle, whatever you want to call it. So what you're doing is eliminating the noisy data and hopefully keeping enough of the other data that you can use. So that's a personal preference. I would say 10 degrees. The new equipment handles it real well. And the summary, okay, 4 things, these 4 things. Just remember these 4 things. Always have redundancy, if you can, with different satellites. Best answer is usually the average of the 2 shots. Get more if you can. Next time you visit the site, get a shot on it again. You know, it doesn't hurt. For important points. For important points. Critical when you use single base, but equally important with a network to make sure you have the right initialization is to get a check shot from the start on something that you know. And if you can, do it as you go. If you pass a known point, if you've been surveying for an hour, maybe you've dropped initialization a couple times and had to reinitialize. Well, as you go by a known point, just hit it. You know, it's not going to hurt anything. It only takes a couple seconds. And then you can see, oh, wait, whoa, 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 I'm 3/10 there. But I was only 500s here. So then it gives you a check, you know, as you go. And again, when you end your session, just get another little check shot, just to make sure. Because you're probably going to lose initialization a couple times if you're on a site. Especially if you drive, because you can throw it in the back of the trunk and drive. Okay, so check shots, redundancy. Multipath, we talked about pretty extensively. That's going to vary for the rover, right? You can't plan for it. You don't know. You don't know where you're going to be. So just be aware of it. When you set a point, set it in the open. Set it away from signs and structures, okay? And then communication. Just make sure you have continuous strong communication as you locate a point. That's for an important point. You can get away with some of the other stuff, but for important points, you want to do that. You want to do those 4 things.